We'll continue with our applications of algebra using Maxima. And in this video, we're going to talk about simple binomial and trinomial equations. Equations that can be factored, simplified, and found the solution for them. And so we start by opening up a worksheet, a Maxima worksheet. For example, suppose we're going to solve this. Okay, we identify that as a difference of squares. I define the equation here and factor it, replacing it in the EQ, and I find three factors there: x minus 2, x plus 2, x squared plus 4. Now this factorization is for real numbers only, and so that's how far the factorization can go. We can identify immediately x equal 2 as a root right here, because x minus 2 must be equal 0. So that gives you x equal 2. X plus 2 also must be equal 0. And so x equal minus 2 is another root. And then the third case, you have x squared plus 4 equals 0, which you can rewrite as x squared equals to minus 4. To solve for that, we can use solve, and we find that the solution is minus 2i plus 2i. And so the four solutions of this equation are like this. Now there is a function that I didn't include here, but it's called g factor, that can be used to should be x to the fourth power. That can be used to factor out everything, including complex numbers. So it's opposite to the one different than from factors, g factor, and that will give us the four factors, including 2 that has imaginary numbers in them, and then we can identify the 4 roots there in that factor. Oh, I actually had that already typed in there, so let's do it again. Solve x cubed minus 27. Factor that, and I find a linear factor here. Will tell me that x will be equal to 3, and then I have a quadratic equation that I can solve using the quadratic formula with a equal 1, b 3, c 9. Calculated determinant and calculated 2 roots, and these 2 roots give me a value related to these are complex numbers. So 2 of them are complex numbers, 2 complex numbers, and the third one is of course x equal 3. Those are the roots of that cubic polynomial. The number of roots in an equation. This is something called the fundamental theorem of algebra, and it says that if you have a polynomial whose coefficients are real, then you're going to have as many roots as the degree of the polynomial. So a quadratic equation has 2 roots, a cubic equation has 3, and so on. For example, let's say we want to find all the cubic roots of the number 1. So basically we're going to try to solve x cubed equal to 1, or x cubed minus 1 equals 0. So there's a polynomial right there that we can factor. And it shows x minus 1 equals 0, which means x equal 1 is one of the roots, and then the other one is the roots of x squared plus x plus 1 equals 0. It's a quadratic equation. We can identify a, b, and c, find the 2 roots. So the solutions are these 3. We could try it. I'm going to copy this. And before this example, I'm going to put the g in front of it. And that is not going to help us. It doesn't do the factoring because the roots are a little more complicated. So this we're not going to help us. But the way that we did it was good enough to solve that problem. How about this one? X cubed minus 729 equals 0. I forgot the equal 0 here, but we can put it now. And it says, okay, you have 4 factors. 2 of them are linear, so that gives me x equal 3 and x equal minus 3 immediately as roots. And then you have 2 quadratic equations. The first quadratic equation has these values for a, b, and c. And I'm going to use that to calculate my roots, and the roots are these values. If you want to see, for example, for x1 and x2, you can try this Richt form of x1. I think it's just going to repeat the same value. The only thing that it does is separates them. And then if you do the float of the rectangular form, it will show that number as a decimal. And then we can also do for x2 and obtain a different number. We're going to erase this one right here. For the second quadratic equation that we have in as a factor in this problem, we have these values for a, b, and c, and we find the roots to be these results. Okay, so those are binomial equations of the several orders done by factoring. And again, not all can be factored, but these are examples that can be factored, and we can find the roots. Let's concentrate into a trinomial equation. I'm going to clear out the values of a, b, c, and u, because we're going to use it later on. And I'm going to try a generic equation that looks like a quadratic in the sense that this is raised to the 2n and this is raised to the n. And so, for example, n equal 2, we get a biquadratic equation or quadratic equation, a squared b squared plus c. Now, going back to this generic equation, if we make a replacement ux to the n, then this equation becomes a u squared plus b u plus c, a quadratic equation. We know the solution of that quadratic equation, and then what we have to do is bring back the u and make x to the n equal u1, x to the n equal to u2, and solve for the values of n from those equations. For example, this should be text. For x to the fourth minus 37, x to the square plus 9 equals 0. I'm going to substitute the x to the 4 with a u square and the x squared with u. And with that, my equation becomes a quadratic equation with these parameters. And I find my roots equal to 9 and 1/4. But I do know that x squared is equal to u, and so that means x squared equal to u1 and x squared equal to u2. Basically means x squared equal to 9, x squared equal to 1/4. Now, I know that when I take the square root of an equation like this, I'm going to get the square plus or minus the square root of this value. So what I did here is just calculate the square root and then use the negative, square root and negative. So these 4 are roots of the quadratic equation that was given over here. Here's another example. We're going to factor the left hand side, and that immediately gives me my solutions 4 and minus 4. And then for here I can solve for x3 will be the square root of minus 2/3 and the negative value of that. So that's the 4 rows right there. You can always check the solution by using solve equation, and I get the same results as I had before. Let's clear up again the values of a, b, c, and d, and we're going to try these equations. Okay, so what we're trying to do here, if we are given an expression that includes the square root of another number plus a number that doesn't have the square root right under the first radical, I want to write them as the sum of 2 terms, square root of the sum of 2 terms, and if it's minus sign in here, I want to use a minus sign here. This is my equation 1, this is my equation 2. If I add them into equation 3, I get this result. And then I could find what the value of x is by raising both sides to the square. And I'm going to switch the order and expand this value. We have a couple of terms here that if we put into the subradical quantity, that should give me a square root of a squared minus b. So these 2 terms here is the square root of a squared minus b. I'm going to call that quantity m. And then x is going to be equal to 2m plus a. If I divide that by 4, I get x equal m plus a over 2. Now we go back to the first two equations that we started with over here, and we're going to subtract them now, because that will isolate y over here. Then we do a procedure similar to the one before, squaring, using the value of m again. And y turns out to be equal to a minus m over 2, or minus m minus a minus m over 2, or minus m minus a over 2. So I have the values of x, m plus a over 2, and y, and get those results. And remember that we were trying to find the expression of these terms as the x squared root of y plus x. And so if I go for the positive values, I find that this is going to be equal to m plus a over 2, a minus m over 2, whereas if it's a negative, it's going to be square root of m plus a over 2 minus a minus m over 2, with m, remember, being the square root of a squared minus b. Now transforming these into this will be okay only if this term m is a perfect square, because if it is not a perfect square, you're still going to have a square root in here, which is what we're trying to avoid here. And so let's, for example, look at this case. Sorry. Shift and enter, shift enter here. And here a is equal to 5, and b is going to be equal to whatever goes inside here. When we put that 2 inside, it goes to 4, so that should be 24. M will be equal to 1, and then the result will be the square root of this. Which is the same as saying the square root of 6 over 2 plus square root of 2. And so we were able to convert this result into this just because m happens to be a perfect square. Here's another example. In order to get these 2 inside the square root, we have to multiply squared. And so a is equal to 7 and b equal to 40. M turns out to be equal to 3, which is a perfect square. And so the result is square root of 10 over 2. Now I want to simplify this. I just write simplify, and I get square root of 5 minus 2. A few cases will be able to do that like that, but the procedure is as presented in here, and it's basically these two equations plus the definition of this value of m for the case in which we want to express equations where there is a double radical in terms of the sum and subtraction of radicals. And so these are the few of the examples that I wanted to present for binomial and trinomial equations. This doesn't cover every single binomial and trinomial equation, some special cases that can be easily solved using factorization of the quadratic equation and then conversion of the radicals as presented before. And so with this way we finish this video on simple binomial and trinomial equations.